Although the first person that may come to mind when someone says physics is Newton, Galileo contributed a lot to the basics of mechanical physics. At the young age of 17, Galileo entered the University of Pisa to study medicine. In a cathedral at Pisa, he noticed a lamp swinging at a constant rate no matter how big the swing. This was the beginning of his interest in physics and mathematics. Galileo's interest sparked even more when he overheard a lesson in a geometry class. From there, he further continued his studies in physics and mathematics. Aristotle's teachings were the most popular before Galileo's. Aristotle was a Greek philosopher and scientist who also contributed a lot to physics. One of his theories was that weight correlates to the speed of something if it is dropped, and that elements want to be close to each other, and that's why a stone falls to the ground and smoke rises to the air. This is what Galileo was taught, and he didn't question it until he conducted experiments of his own regarding dynamics. One of said experiments was dropping two objects of different weights from the top of the Leaning Tower of Pisa and observing that both objects reached the ground at the same time. From this, he came to the conclusion that acceleration due to gravity is independent from the weight of the object, which later helped develop Newton's theory of gravitation. One law Galileo helped develop was the law of inertia. Aristotle believed that objects only moved if there is a constant force on them, and as soon as that force was removed, the object would stop. Galileo debunked this using his ramp experiment. In his experiment, he put a ball on a ramp and noticed that the ball would come relatively close on the other side to its original height. He concluded that the less friction present, the closer the ball gets to its original height. This later helped Newton develop his first law where objects at rest stay at rest, while objects in motion stay in motion if there is no net external force. In this case, the net external force is friction, and that is why the ball doesn't come to the exact height. Newton, the man famously known for the laws of motion and gravitation published in his Mathematical Principles of Natural Philosophy, conducted his experiments partially due to encouragement from other scientists, and partially due to his belief that he could figure out how God created the universe. He is quoted as saying, "When I wrote my treatise about our system, I had an eye upon such principles as might work with considering men for the belief of a deity, and nothing can rejoice me more than to find it useful for that purpose." He hoped his scientific writings would lead people to think about and believe in God. His three laws of motion would become the basis of mechanics, which is defined as the branch of applied mathematics dealing with forces and forces producing motion. Said laws governed how things move and why. In his mathematical principles, Newton reduced all the objects he was observing to mathematical points without size or rotation, which allowed him to neglect forces such as friction and air resistance. Neglecting those forces meant he could demonstrate his theories in terms of only mass, length, and time. The first law is often stated quite simply that objects at rest stay at rest, while objects in motion stay in motion. Although that is not incorrect, it is missing a piece. Objects will exhibit these behaviors unless acted on by net external forces, which cause change in movement. The second law, which gives one of the essential physics equations force equals mass times acceleration, or acceleration equals force divided by mass, states that acceleration is produced when force acts on a mass. The third law sounds the most complicated, but in practice is actually quite simple. For every force, there is a reaction force that is equal in magnitude and opposite in direction. Essentially, if something is pushed, the object it is pushed against resists it with a force of the same amount, but in the other direction. Newton's laws of motion can also be applied to conservation of momentum. You can change force equals mass times acceleration to force equals momentum over time, because momentum equals mass times velocity, and velocity divided by time equals acceleration. The third law explains why momentum is conserved in a perfectly elastic collision, because the masses in said collision exert equal and opposite forces on each other. As well as his famous laws of motion, Newton also formulated a law of gravitation. The modern legend goes that he discovered gravity when an apple fell off a tree and hit him in the head, but modern scholars believe this isn't true. However, a manuscript written by William Stuckley does mention his observations of apples falling off the tree and their conversations about things always falling towards the center of the earth. The law of gravitation, which is represented by force of gravity equals the gravitational constant times mass 1 plus mass 2 divided by distance squared, says that every object in the universe attracts every other object, and that the gravitational force between two objects is proportional to the sum of their masses and inversely proportional to the square of the distance between them.